Now, up to this point, we have been exploiting the relationship between definite integral and area in one direction. We have always been using the definite integral to calculate the net area, or as in the previous example, to calculate the total area. Now that's all well and good when your integrand is a function whose antiderivative is easy to find. But what if you have a function like this one, square root of 4 minus x squared, whose antiderivative is quite difficult to find? This is not a polynomial, this is not a sum of regular basic trig functions, this is not a sum of regular exponential functions. This particular quantity is quite difficult to find the antiderivative, and if you don't believe, I actually challenge you to pause for a moment and to see if you can find the antiderivative of the square root of 4 minus x squared. Now, even if you're having some trouble, which is not unusual at all, this definite integral can be evaluated without using an antiderivative at all. And that's by instead trying to see if it's easier to calculate the area under the graph of f of x equals square root 4 minus x squared, which is an upper semicircle of radius 2. Because this graph is an upper semicircle, we can use a high school geometry formula to get the area under this graph. The net area would be, the entire circle would be pi times the radius squared, but since we only have the upper half of the circle, I would cut the result by 2. Therefore, the net area is 2 pi. And because of the fundamental theorem of calculus, which says that that definite integral and this net area are the same, we can conclude that the integral from -2 to 2 of the square root of 4 minus x squared is equal to 2 pi. And we were able to conclude that just with geometric area formulas and without having to find an antiderivative at all. Very neat trick.